Hello, my name is Rafael Felipe, and I'm here as a speaker of their article, The Effect of High Temperatures on Steel Fiber Reinforced Concrete. The authors are Rony Agra, Ramel Serafini, Antonio Figueiredo, and I, from the Department of Civil Construction of the Polytechnic School of the University of São Paulo. Fires are the great motivation. They can increase structure temperature. In the case of concrete structures, they can change the mechanical properties of the paste, especially reducing its strength and increasing its fragility. So the concrete becomes much more fragile. The fiber's goal is to improve this fragile behavior. They sew the matrix, ductilizing it. The use of fibers is increasing in Brazil, especially in tunnel lining, a situation in which the fire is crucial. In addition to the ductilization, fibers promote the increase of residual tensile strength. In other words, the increase of post-cracking strength. A major guide for FRC is the FIBE Model Code 2010, published in 2013, which provided a great guide to design of structures of FRC. To characterize the FRC, we have the flexion test, which offers results against safety, because at the fibers act in tensile strength and there is no pure tension, only flexion, there is a portion of compression adding the resistance. In addition, the specimens are large prisms, which are difficult to handle, especially after being submitted to high temperatures, which makes the concrete matrix fragile. There is also the double puncture test, but it causes crushing of the matrix and its analysis is difficult, since the crack, which is a difficult area to be measured, is complex. Finally, there is the Deuce test, double edge wedge splitting, proposed by the Prisco in 2013, a test with a more difficult preparation, but which provides results that are easy to read. It was the method used in this research. The literature on FRC at high temperatures is very scarce, and the published articles refer to the matrix of high resistance. In this research, we used low strength concrete, class C25, common in the city of São Paulo and throughout Brazil. We use as material for molding high initial strength cement, artificial sand, gravel 1, super plasticizer additive, and short cold drawn hooked end steel fibers in a content of 25 kilograms per cubic meters of concrete, and a water cement ratio of 0.58. The dosage of all materials is in accordance with the table shown here. A plant produced the concrete, and a concrete mixer truck carried out the transportation to the lab. The slump test resulted in an 80.5 centimeters reduction. Removed from concrete for order purposes, 19.2 kilograms of fibers were added in 762 liters of concrete, resulting in 25 kilograms of fibers per cubic meters of concrete. The specimens were molded in steel shapes with wooden wedges fixed on the sides. These wedges are 2 centimeters wide and 45 degrees open. 12 cubic specimens with a 10 centimeters edge were molded for the Deuce test, and 4 cylindrical specimens with a diameter of 10 centimeters and a height of 20 centimeters for the compressive strength test. All forms were greased with oil to facilitate stripping. All specimens were taken to the vibrating table for approximately 60 seconds and then covered with a plastic canvas. The stripping occurs after 40–80 hours. After the stripping, water was sprayed on the specimens that were again covered with plastic canvas for 60 days. The cylindrical specimens were submitted to the compressive strength test at the age of 28 days in a Shimadzu press with a compression rate of half megapascals per second. After curing for 60 days, a groove was made in the vertices of the wedges, 5 millimeters deep and 2 millimeters wide, in order to induce a type 1 crack. After grooving, the specimens were heated in an industrial Jenga oven. A group of 4 specimens are kept at room temperature to establish a reference. A second group of 4 specimens were heated at 300 Celsius degrees for 80 hours, and a third group heated at 600 Celsius degrees for 4 hours. After that preparing, the dose test itself was done. It is a direct tensile test where a type 1 crack of pure tension is induced and enabling easy analysis. To measure the crack opening, 2 clamp tensiometers were attached with elastic on opposite faces of the cube, perpendicular to the crack plane, as can be seen in the photo. An electromechanical press EMIC with an open system for speed was used, with a loading speed of 0.12 millimeters per minute. To avoid interference with the results, a 3 centimeters diameter steel roller is used between the press and the hub, supported by the surfaces molded by the wedges. In these surfaces, steel sheets are fixed and powdered graphite is spread to reduce friction. As a result, there was no spalling on any of the specimens during heating, neither crushing of the matrix during compression, indicating that it uses an efficient test that provides representative results. At 28 days, the compressive strength of the concrete was 28 megapascals, with a standard deviation of 0.9 megapascal, confirming that the concrete is in fact class C25. Here are the tensile strength curves as a function of cracking opening. The 3 interesting points to note are the peak resistance, the crack open at half millimeters and 1.25 millimeters, which characterize the SLS and the ULS respectively. We see the first image at 25 Celsius degrees, 300 Celsius degrees, and 600 Celsius degrees. At 600 Celsius degrees, there is practically no peak. The average values of these curves are plotted here. Peak resistance at break in black, residual tensile strength in SLS in blue, and strength in ULS in red. A reduction in resistance is observed with an increase in temperature. Then, what is noted is that at 300 Celsius degrees, the peak resistance has a big reduction compared to the ambient temperature. But the residual strength does not suffer a big reduction. This is because at 300 Celsius degrees, the paste is already deteriorated due to thermal degradation, cement dehydration, efforts of thermal origin, and change in the pore distribution. Therefore, the paste is already fragile. As the peak strength corresponds to the rupture of the paste. What governs this strength is the paste. The steel fibers act little. They start to act in the post-cracking stage, but at 300 Celsius degrees, they still remains intact. Therefore, there is no great reduction in residual tensile strength when comparing temperatures of 300 Celsius degrees and 25 Celsius degrees. At 600 Celsius degrees, the paste deteriorates further, reducing the peak resistance, and it's noted that there is practically no peak. In addition, the steel is already deteriorated. Therefore, the fibers that have the role of sewing the matrix do not sew as well, reducing the post-cracking strength. What you observe then is that the fibers fulfill their role after rupture, ductilizing the structure and preventing a fragile collapse, increasing the safety margin for a temperature of up to 300 Celsius degrees. In addition, this proved to be an efficient methodology also for low-strength concretes. A type 1 crack was induced, implying an easy analysis of the results. And the tensile strength of the matrix has been reduced by 50.96% and 93.75% for temperatures of 300 Celsius degrees and 600 Celsius degrees respectively. For the SOS with a crack opening of half millimeters, the resistance did not change significantly to 300 Celsius degrees, and it suffered a great reduction of 75% to 600 Celsius degrees. And for the ULS, the residual resistance to 300 Celsius degrees suffered a small reduction of 6.12% and to 600 Celsius degrees, a great reduction of 81.63%. Thank you very much.